Welcome back to everybody. I hope you enjoy your coffee break. So let's start now the second part of our webinar dedicated to two other EU-funded projects. We will start with our first speaker, Mahesh Suresh from the SELFIE project. Mahesh, I will leave you the floor to share your screen.
Hello, Evelina.
Hello.
Hello. Good morning to everybody. So I will present selfie-related updates. Just I will share my screen. Okay, is it visible?
Yes, perfectly.
Perfect.
You want to, you can just put it in presentation mode.
Yes.
So we can see it full screen.
Okay, I think it should be visible now.
Yes, perfectly. Thank you.
Perfect. Okay. So my name is Mahesh Suresh Patil. I am Project Technical Coordinator at Vrije Universiteit Brussel, VUB. Today I will be presenting about SELFIE project, which is a short title for self-sustained and a smart battery thermal management solution for battery electric vehicles. So let's just dive in. The scope of the presentation is introduction of the SELFIE project, aims and objectives, targeted results for industrialization, innovations related to the SELFIE project, and the achievements so far in the SELFIE project, and what is the project outlook in coming months. So this is what I will be presenting. So let's go to the introduction. SELFIE project is innovation action type under the call H2020 LCGV 012018 and as explained, title is self-sustained and smart battery thermal management solution for battery electric vehicles. The project is coordinated by VUB and it has started in December 2018. The project is supposed to be finalized in after 51 months, that is February 2023. There are 10 partners from 8 countries. I'll just list them. Valeo from Germany and France, VUB from Belgium, Virtual Vehicle from Austria, Ikerlan from Spain, FEV from Poland, Fraunhofer LBF Fraunhofer from Germany, IMECA from Turkey, I2M from Austria, FCACRF from Italy, and AIT from Austria. So these are the partners which are involved in the SELFIE project. So what are the aims and objectives of the SELFIE project? The aim of the SELFIE project is to develop and demonstrate a novel self-sustained compact battery system, which consists of a smart modular battery pack, which has cooling system and thermal storage system as a heat buffer capable to absorb excess heat due to fast charging. Also, it will have excellent internal thermal conductivity to enhance overall heat transfer. The second aim of the project is it should have it will have an advanced battery thermal management system that is capable to keep the battery temperature effectively within the optimum window, and also to prevent overheating and along with that a battery degradation due to fast charging. So these are the aims, and the targeted results for industrialization are listed here. It has been divided into 4 parts, and as you can see that there are 2 major points which are very much relevant for EV growth of EV. One is user acceptance, and second is EV market penetration. And basically the 4 divided parts are very much related to it. First is the enabling fast charging up to 5C. Which in our case will go in up to 140 kilowatt of charge power, and reducing the charging time to 10 minutes. That is almost 2 to 3 times faster than the today for a 30 kilowatt battery pack. By developing a battery system capable to effectively absorb the excess heat during fast charging. Also, this will allow us to enable a long-range driving by employing a battery pack capable of handling charging powers up to 140 kilowatt instead of current 50-100 kilowatt range. And the target is to have a battery. Target is to have a long range in the terms of 700 to 1,000 kilometers. Another aspect of the project is the overall cost reduction by 30% at the pack level by simplified design of the battery system, and it can be translated into 10% reduction of the total vehicle cost. And the fourth aspect is preventing the premature degradation of the battery and effectively prolonging the battery lifetime by keeping the battery temperature effectively within the optimum temperature during fast charging as well as during the driving case. So what are the innovations in the SELFIE project? First is a new smart heat storage housing. This deals with smart and cost-efficient material structures, including polymers, phase change material, and inserts. Second is novel battery cooling plate, which enables high heat transfer rate and good thermal connection from the battery to the cooling and heating system. Novel PCM heat buffer dedicated for fast charging that is integrated in the body of the vehicle. Innovative cooling module in the front end. This is from the aspect of increasing the airflow rate and decreasing the energy consumption. And development of a cold storage device that will allow us to increase the power of air conditioning system during fast charging and increase the system efficiency. And finally, we have done the virtual safety validation with hazard and operational study and risk assessment. So what are the achievements so far? We have done in-depth characterization of various cells in terms of heat generation, diffusion, and accumulation. And then we have done it in calorimeter to check what is the performance of the cell, and we have compared it. And after that, we did a selection. We had some selection criteria based on the battery requirements versus the cell technical specification and testing. We did electrical characterization as well as thermal characterization based on nominal capacity, rate capability, and internal resistance. And in the last stage, we did testing for aging and lifetime and safety and cost as well. And we come up with that for our project, Toshiba 23 ampere cell would be the LTO cell would be the best. We have developed a thermal management system and it has started with design and then prototyping of the component system for battery thermal management. It has been divided into two parts. First part, or I would say first group deals with the battery pack assembling and housing, which is responsible for a single battery cell testing, prismatic LTO Toshiba 23 ampere cell, then battery module. And module consists of number of cells forming thermally independent unit, then cooling plate design between the battery modules and battery cells, and then battery housing, which consists of two compartments, which has a PCM heat buffer at the bottom of the housing. So you can see here the design, modeling, and then detailed design and the modeling, and then you can in the third column you can see the prototyping of actual which will be integrated into actual demo vehicle. The second group deals with the thermal system, specifically front-end module, which consists of low temperature radiator, evaporator, condenser, inlet guide vane and shroud, fan system, as well as a cold storage device, which includes PCM and refrigerant pump and control strategy. So here also we have developed which has high air mass flow rate radiator. Again, the work package 3 here, which deals with the second part of the thermal management system, is divided into 3 parts. First part is system development, which is the development of efficient refrigeration system or loop development, and then optimization of battery thermal module or pack platform, and then packaging constraint for thermal management system circulating. I just want to point out here that the SELFIE project is actually converting IC engine vehicle into BEV, so we have space constraint and weight constraint. So from that aspect, battery pack assembly and refrigeration system development has a lot of constraint. It needs to be optimized to the specific case. The second part deals with the cold storage device. It is prototype ongoing, and we have developed first prototype, then we have tested it, and for higher efficiencies we are upgrading it, and it has been tested for structural integrity and thermal performance as well. And the third point deals with the system control development, which is ongoing activity for optimization of and a reduction of a cooling power. One of the aspects of the project was to study the thermal, electrical, and mechanical characterization at the module level. So what we did is we did a setup of a experimental setup for a module, and then we tested it, and we achieved a result which shows that thermal management is efficient at 4C fast charge. It can keep the temperatures below 35. Which in our case, which was around 32. And then we also did a computational study. We developed a model, we validated it, and then we optimized it. And these changes will be integrated at a pack system level. And here at the left corner, we can see the radar chart, which compares natural convection, only PCM cooling, and then PCM and liquid hybrid cooling. In our case, here the module is cooled by the cooling channels by sideways, and PCM plate is there at the bottom. Regarding the actual vehicle integration, this process is ongoing. For the testing and performance checking, we have already conducted a comprehensive test on a baseline vehicle, Nissan ENV 200, which is electric vehicle, and we have conducted extensive cabin cooling demand and performance testing, as well as cabin heating demand and performance testing. And once the demo vehicle in Fiat Doblo, when the battery will be integrated as well as efficient thermal management system will be integrated, the results will be compared and checked what is the update, what is the increase, how much increased efficiency we can get in terms of performances. These are the open access publications which you can refer already. We have already published nine journal articles, as well as we have participated more than 15 conferences and workshops. So if you would like to know more, you can go through these publications. I'll just present what is the project outlook. In terms of technical terms, battery pack assembly is ongoing activity. We have received all the components needed for battery pack assembly at VMACAR campus, and then the battery pack assembly will be completed in coming months, and as well as thermal management system also. Thermal management system components delivery also is expected soon, and then in the mid of 2022, the vehicle will be the components which developed on the SELFIE project will be integrated into demo vehicle, and then for the rest of the project, it will be divided into two parts. One is control system development and debugging, and then it will be tested for TRL level 7. So you can see here we are in the month of 40, and we are actually prototyping, assembling, and integration, and soon we'll start demo vehicle testing. So what are the mid to long-term impacts of this project? So one of the objective is to have a market introduction in 2023 to 2025, and the full objective, in a sense, it will be seen in 2030, where we have more market penetration and more user acceptance. So this is all from SELFIE, and if you have any questions, queries, please contact me or Ilaria, who is a dissemination leader for SELFIE. We have here given LinkedIn and mail communication contacts, and also website. So that's it for SELFIE, and thank you for listening.
Thank you very much, Mahesh, for the very interesting presentation on developing such close to i-HeCoBatt project. So we'll leave the questions for your project at the end. Aldo Sorgnotti from MULTI-MOBY project. Aldo, the floor is yours. Thank you.
Thank you very much. I try to share my screen. Hopefully you see my screen.
Not yet in presentation mode, but we can see your screen.
Now
Yes,
it should be in presentation mode.
Perfect.
Okay,
Thank you.
good. So I am Aldo Sorgnotti. I am from the University of Surrey in the United Kingdom. I am the dissemination leader for the MULTI-MOBY project. First of all, let's have a look at the general consortium setup. We are a consortium including 9 participants. The coordinator is Infineon Austria. The duration of the project is 3 years. The project started in December 2020, so we are still differently from the previous project that have been presented in the first part of the project execution. The total budget is approximately 8 million euros. The target of the project is to implement safe, secure, high-performing, multi-passenger and multi-use affordable electric vehicles. In particular, you can see some initial rendering of these urban electric vehicles for the transportation of passengers and goods that we included in the project proposal. In particular, the target of the project is to implement a small fleet of vehicles, in particular 3 multi-passenger 4-door M1 vehicles with a 4-wheel drive on-board centralized powertrain architecture. So the motors are actually installed on the sprung mass of the vehicle and the vehicle body, with 2 15 kilowatt 100 volt air-cooled high-efficient powertrains using permanent magnet assisted synchronous reductance motors, so motors with low content of permanent magnets. And then the project is also developing other 3 vehicles that are multi-purpose vans. In terms of homologation categories, one of them is under the category L7E CU. It will be 4-wheel drive with 7.5 kilowatt 48 volt air-cooled powertrains, including a low-cost belt-based transmission system developed by Valeo, that is one of the participants of the project. And then the multipurpose vans also include 2 vehicles that are under the category N1. Also, these vehicles are 4-wheel drive, one with 2 15 kilowatt 100 volt air-cooled powertrains developed by Dana TM4, that is one of the consortium participants, and the second one with 2 15 kilowatt 48 volt liquid-cooled powertrains, again developed by Valeo. One of these vehicles will be for the transport of general goods, while the other 2 vehicles will target the delivery of food. Here you can see some initial CAD models of the vehicles that we put together in the initial phases of the project, but now, despite we are still in the first half of the project execution, there are already the initial prototypes of these vehicles that are available for preliminary assessment. In terms of electric powertrains development, as I said, there are 2 series of electric powertrains that are being developed within MULTI-MOBY, and there are also the result of an evolution involving the previous European project TEL. So there is a series of 100 volt electric powertrains developed by Dana TM4, and the second series of 48 volt powertrains developed by Valeo Powertrain Systems. During the project, there are simulation-based optimization activities, for example, in order to improve, to optimize the geometry of the rotor of the electric machines, but there is also significant testing activity on test rigs as well as directly on the preliminary versions of the vehicle demonstrators. For example, here you can see the Daimler TM4 electric powertrain installed on the initial vehicle prototype. You can see also some of the components in terms of motor and inverter that have been developed by Vrije Powertrain systems. It is possible to see the mule, the chassis with the powertrain that is being tested at the rolling rod facility available at the participant IFES, that is actually the vehicle integrator within this project. And also we have carried out some testing on a test track in order to assess the drivability and also to fine-tune some of the controllers that are being implemented for the operation of these light urban electric vehicles. One of the main features of these multi-MOBY vehicles is safety. Safety means, first of all, passive safety. In particular, one of the participants of multi-MOBY, that is CIDAUT from Spain, has been responsible for the optimization of the high-strength steel structure of the vehicle chassis with a high energy absorption capability and very high stiffness. These chassis include different products of the dual-phase steel family, and it has been designed through the combination of finite element analysis followed by physical clusters. So here we can see some of the models for simulating crash scenarios that have been developed by the participants CIDAUT or the consortium. And then in these photographs, we can see examples of clusters that have been physically implemented in December last year at the CIDAUT facilities in order to assess the passive safety performance of the vehicle. Multi-MOBY also includes consideration of some innovations in terms of active safety performance of the vehicles. In particular, the target is to enhance the active safety of the vehicle through simple, cost-effective solutions, including consideration of vehicle connectivity and partial driving automation. So, for example, a typical scenario that is addressed by multi-MOBY is the scenario in which, for some reason, because of an evaluation error of the human driver or the semi-automatic driver system, the vehicle enters a corner at excessively high speed. If we have this situation in a conventional human-driven vehicle, we have that even if the SP will intervene within the corner in order to stabilize the vehicle so that the vehicle doesn't spin, doesn't develop a high value of size dip angle, nevertheless, even with the SP, the vehicle, if the driver makes an evaluation error and enters a corner at excessively high speed, will not be able to follow the desired trajectory, with potential risks in terms of road safety. So the idea of multi-MOBY is to benefit from the fact that nowadays vehicles are characterized by the info navigation system that can allow to know the current position of the vehicle. So the idea is that by knowing the position of the vehicle and by knowing the curvature ahead of the road, the expected curvature ahead, it is possible to preemptively slow down the vehicle if we see that the vehicle is going to enter a corner at excessively high speed. So this is the concept of the so-called preemptive braking controller that has been implemented within multi-MOBY. So essentially, it doesn't need a complex actuation because it is only a matter of reducing the torque demand independently from the driver input and possibly implementing a pressure level on the four calipers of the vehicle, but it doesn't need independent actuation, for example, the friction brakes. It doesn't need any specific more complex chassis actuator than a conventional production passenger car. essentially the idea is to slow down the vehicle preemptively by using some form of predictive control if the vehicle speed is excessively high with respect to the trajectory ahead. We have carried out an extensive simulation activity in order to assess this functionality in the first part of the project, and despite we are still in the first half of the project, we have also been carrying out some preliminary tests of this preemptive braking control functionality. For example, we have implemented this preemptive braking control functionality in the form of different controller formulations at different levels of complexity with the MULTI-MOBY. The most basic implementation is called preemptive rule-based trail braking controller, and then we have two nonlinear model predictive controller implementations of this preemptive braking control function that are at a higher complexity level. But essentially, a typical example of operation of this controller is in a U-turn maneuver. So X and Y represent the coordinates of the area where the vehicle is moving. The passive vehicle is accelerated by the human driver. The human driver tries to make the vehicle follow the reference trajectory by steering, but as the vehicle speed is excessively high, the vehicle is not capable, without preemptive braking control function, to follow the expected trajectory. Whilst with the preemptive braking function, we can see that the vehicle, before entering the corner, is slowed down at a speed that is compatible with the curvature radius, and then at the exit of the corner, the preemptive braking control system is switched off, and as a consequence, the vehicle reaccelerates because the vehicle follows again the human driver input. So this is a very basic example of operation of this simple additional safety control function that has been preliminarily evaluated in MULTI-MOBY. Another concept that we are testing in MULTI-MOBY is, for example, to augment the traction control function of the vehicle that prevents wheel spinning in acceleration conditions by using tie rod friction preview. So the idea is that with vehicle connectivity, it is possible to know potentially in advance the presence of low friction patches on the road. And as a consequence, we can integrate this map of the future friction conditions of the road within the traction controller of the vehicle that reduces the torque demand of the electric powertrains when there is a risk of wheel spinning. And the benefit of this functionality, of this road preview functionality, is that we can preemptively reduce the powertrain torque before the wheel reaches the low friction patch in such a way that despite conventional electric powertrains are characterized by significant actuation delays, we don't have any safety issue in terms of vehicle dynamics when the vehicle travels on low mu patches. And again, also for this functionality, we have already carried out some preliminary experimental testing. In particular, this is a picture of the vehicle prototype that has been tested with the MULTI-MOBY in the car park of our university. We can see a test where we have a transition from a high tie rod friction condition to a low tie rod friction condition. And here aside, we can see some experimental measurements during the test. I will not go through the details, but in the central plot here, we can see this variable KRL, that is the slip ratio of the rear left driving wheel. And essentially, we can see that for the passive vehicle, indicated by the letter P, we have a significant increase of the slip ratio after the transition from high to low friction conditions. For the case of a conventional, called base U in this figure, of a conventional traction controller, we have some form of reduction of the slip of the wheel after the transition from high to low friction, but this reduction is quite moderate because of the powertrain actuation dynamics, whilst for the case of the controller with the benefit of V2X connectivity, so by knowing in advance the variation of the tire rod friction condition, it is possible to significantly limit the slip ratio of the tire, on the driving tire, after the transition from high to low friction. And this is only an example of preliminary testing. Now we are carrying out further activity to robustify the algorithms, and we are also testing them on the vehicle, on the multi-MOBY vehicle prototypes prepared by the participant HiFers. So we also published a journal paper describing the details of this activity. So I hope that with this short presentation I provided a flavor of what we are doing within MULTI-MOBY. Nevertheless, you can follow us on our website, on Twitter, as well as you can contact the coordinator or myself if you are curious about and you would like to have further information about our project. Thank you very much for your attention.